Hello and welcome to our first video. In this video we will introduce you to capacitors. To explain the basics of a capacitor we will start with how it is constructed. Then we will go through the physics of a capacitor. Also, we will cover a few important basic equations. Finally, we will talk about different types of capacitors and some of their applications. If you enjoyed this video, please don't forget to hit the like and subscribe button to our channel for more upcoming videos. Here you can see the construction and the main elements of a plate capacitor. It consists of two parallel conductive plates that are separated by an air gap or insulating material called dielectric. To understand how a capacitor functions, first we need to build a circuit. To do so, let's connect the conductive plates to a copper wire and use a DC power source, in this example an AA battery, to complete the circuit. As soon as power is applied, current starts flowing and the capacitor charges up. This means the plate on the capacitor that attaches to the negative conductive plate of the battery accepts electrons that the battery is producing, and the plate on the capacitor that attaches to the positive conductive plate of the battery loses electrons to the battery. Before moving further, it is necessary to clarify one point in this animation. In reality, the positive charges or protons, shown with red circles, really don't move. However, to better demonstrate this phenomenon we are showing positive charges, or protons, moving to the positive plate, which would represent the loss of electron to the battery. In our next electronic basic video this phenomenon will be demonstrated in detail, so please make sure to subscribe to be notified when the video is available. So, once it's charged, the capacitor has the same voltage as the battery. As AA battery has a 1.5 volts, it means there is a 1.5 volts on the capacitor. Now let's look at a few of the basic but important equations. The most important quantity to describe a capacitor is its capacity, or C, measured in farad. It is abbreviated by a capitalized F. It can be calculated by the ratio between the stored charge, or Q, and the applied voltage V. Also note, in this case Q denotes the stored charge of just one of the two plates. Either the minus side or the plus side, but never the sum of both plates' stored charge. Alternatively, the capacitance can also be computed by the second equation. The other important parameter for a capacitor is the electric field strength, or E. The unit for it is either volt per meter or Newton per coulomb. In the case of a capacitor, it is given by the ratio between the voltage level, V, and the distance between the two conductive plates, or the dielectric thickness, D. To understand how electric energy is accumulated and depleted in a capacitor, we need to add a resistor to the previous circuit to make a RC circuit. By applying a voltage to this circuit, an electric field is formed between the plates, which makes the capacitor a way to accumulate electric energy. As shown in the capacitor charging graph on the right side, the capacitor voltage increases until it reaches the voltage level of the source. By then, current cannot flow any longer. The rise in the RC charging curve is much steeper at the beginning, because the charging rate is fastest, due to the higher voltage difference between the battery and the capacitor at the start of charge, but soon tapers off exponentially, as the capacitor takes on additional charge at a slower rate. Although they work in completely different ways, capacitors and batteries both store electrical energy. Thus, if the capacitor is now connected to a resistance, like a bulb here, it can discharge again, and current is flowing back and keeping the light on, until the charge is completely depleted from the capacitor. Like charging, the rate of decay of the RC discharging curve is steeper at the beginning, because the discharging rate is fastest at the start, but then tapers off exponentially, as the capacitor loses charge at a slower rate. As the discharge continues, VC reduces, resulting in less discharging current. Capacitors are divided to fixed and variable. In this video, we will only focus on few examples of fixed capacitors. We will start with the most popular type, the ceramic disc capacitors. First, let's remove the protective coating to have a look inside it to better understand its construction. They have a very similar construction to the plate capacitor we explained earlier. They are made up of two metal plates coated on the sides of a ceramic disc. The metal plates act as conductive plates or electrodes, and the middle ceramic disc acts as the dielectric. The leads are connected to the electrodes by a solder connection. Each lead is connected to one side of the electrode, as one will act as the anode terminal, and the other as the cathode terminal of the capacitor, while connected in a circuit to a power supply. Next, we will briefly talk about three other popular type of capacitors. Since it is impossible to cover all the details in such a short video, we will have a separate video later covering the details of these capacitors. Let's start with the SMD Ceramic Capacitor. Surface mount device, or SMD capacitors, are multi-layer ceramic capacitors. These multi-layer ceramic SMD capacitor consists of a rectangular block of ceramic dielectric in which several interleaved precious metal electrodes are contained. This structure gives rise to a high capacitance per unit volume. The inner electrodes are connected to the two terminations, which one side of the metal layers will act as the cathode terminal, and the opposite side as the anode terminal. Also, the size and the number of layers determines the capacitance of it. They are small, leadless, relatively cheap to manufacture, and have a very low spurious inductance. Thus, they are widely used in high-volume production printed circuit boards. The next example is an electrolytic capacitor. They are popularly known as a polarized capacitor, wherein the anode has more positive voltage than the cathode. The electrolytic capacitor construction involves two thin layers of aluminum or copper foil, the plain foil, and the etched foil. These two foils are separated by a paper spacer impregnated with electrolyte. The electrolyte can be in the form of solid, liquid or gel. To set up the polarity of two foils, they are anodized by chemically growing a thin layer of aluminum oxide to form the anode, and distinguishes itself from the cathode. The oxide layer on the anode will work as the dielectric in this type of capacitors. Due to their very thin dielectric oxide layer and enlarged anode surface, electrolytic capacitors have a much higher capacitance than ceramic capacitors. Lastly, let's look inside a wet tantalum capacitor to understand how it functions. In the construction of this type of capacitor, the center tube called the pellet works as the anode terminal. To form the pellet, a relatively pure elemental tantalum metal powder is compressed around a tantalum wire. The dielectric is then formed over all the tantalum particle surfaces by the electrochemical process of anodization. Wet tantalum capacitors use a liquid electrolyte as a cathode in conjunction with their casing. In general, tantalum capacitors are known for their high capacitance and small dimensions. However, tantalums are generally more costly, have a more limited range of available capacitance and voltage values. We hope you enjoyed this video. Please stay tuned for more videos by subscribing to our channel. Goodbye.